So today I'll be discussing this problem path with maximum gold, which is the Leetcode daily problem for 14th May 2024. So in this problem basically we have been given a gold mine which is called grid of size m cross n, and each cell in this mine has an integer representing the amount of gold that is present in it. So if it is 0, the integer is 0, then it is empty. We need to collect the maximum amount of gold that we can under some constraints. So first constraint being that every time you are located in a cell, you will definitely have to collect all that gold in that cell, right? That is the first constraint. Secondly, once you have collected the gold in that particular cell, you can walk one step to the left, one step to the right, or up or down of that cell. So basically you can travel to its adjacent neighboring gold cells, right? And another thing, you cannot visit the same cell more than once. The fourth constant is basically you cannot visit a cell that has zero amount of gold. And the last constant being you can start collecting and stop collecting gold from any position in the grid that has some gold, obviously, at any point of time. So basically we can start from any non-zero gold cell and then stop at any non-zero gold cell. That's what the last constant is trying to say. So basically what we can do here is we have basically for a particular ij cell, the neighbors will be I minus 1j, which is going towards the up, I plus 1 comma j, which is going down, I j minus 1, which is going to the left, and I j plus 1, which is going to the right. So these are all the options that we have. Once we are at a particular ij, these are all the cells we can go to, right? So what we can do is iterate over every possible starting point, right? It has said in the problem that we can start from any cell in the grid. So we can start from, if we can start from any cell, then we need to run our algorithm for every possible starting point, right? So basically we need to traverse through the whole grid and see if it has non-zero gold or not. If it has non-zero gold, then it cannot be or possibly one of our starting points. So then start from here, and once I am at a particular ij, right, what do we need to do? We need to basically collect the amount of gold that is present in it and then recursively do the same thing for each of its neighbors, right? So if I'm at a particular ij, I will have 4 neighbors, so 4 different paths, and each of those neighbors will have their 4 different paths, so all are a lot of different paths, right? So how do I choose between all these? How do I choose that which path gives me the greatest amount of basically the gold? So we need to maximize the amount of gold. So if we call the function recursively for our neighbors and the function gives us the amount of gold the maximum amount of gold we have collected from each of those neighbors, then we can choose based on the maximum amount of gold we have collected from each of those neighbors and get and choose the path that is giving us the maximum amount of gold, right? That's how we maximize the amount of gold that we collect while going from I comma j to any of its neighbors, right? And another thing, that grid of ij is at minimum 0, right? It is never negative, so it is never a choice to stop collecting gold at any particular ij, right? It is saying in the question that you can stop collecting gold from any position at any time, but it is not going to be in our favor, because if in the worst case we will not collect any gold, but I mean we will not lose out on any gold while traversing the neighboring cells, right? So that's another thing that we need to keep in mind. So yeah, that's mostly about the idea. So let's try to code it. So basically this problem is essentially going over each of the cells that have non-zero gold and run our DFS algorithm. That's it. So let's say I have this solve function and I am at a particular I comma j, and we have that particular grid, and again we need to keep track of all the cells we are visiting in a particular DFS path, right? Because it has said that we cannot visit the same cell more than once. So in a particular DFS path, let's say I'm at this ij, then I'll go to probably, let's say, I minus 1 comma j, and then I might try to come back to ij again in the same DFS path, but that cannot be valid because we have already traversed that in that particular DFS path. So we cannot visit a particular cell more than once. So we need to keep track of all the cells that we are visiting in a particular DFS path. So for that, we need again a matrix, Boolean matrix, which will give us whether we have visited this particular I or j or not, ij or not. So let's call this visited. So yeah, now as I said, each cell, each ij will have 4 neighbors. So essentially we have to run this algorithm for each of the 4 neighbors. So what we can do is, the poor way of writing code will be to run this algorithm by manually typing each of the neighbors for I minus 1j, I plus 1j, ij minus 1 and ij plus 1. So instead of doing that, we can choose to write some cleaner code, and what we can do is we can create displacement arrays in the x and y direction. So dx will be 0 1 0 0 1 minus 1, and dy will be 1 minus 1 0 0. So this essentially means is the first neighbor that we are going to have while we are at I and j will have displacement 1 in the y direction, so I plus 1, y means the row, and 0 in the column direction, right? So j plus 0. Similarly, I minus 1, j plus 0, then I j plus 1 and I j minus 1. So this way we can get all the 4 neighbors without having to manually type the neighbors, right? So this will help us write some cleaner code. Okay, so I am at a particular ij and I am trying to get the maximum answer, right? So let's initialize it to 0, and now let's try to iterate over each of the 4 neighbors. And for a particular dth neighbor, the row index and the column index will be given by, row index will be given by I plus dy of d, and c, which is the column, will be given by j plus dx of d. Okay, once I have that, I need to check if this r and c does not, is a valid row and column index or not, because it might happen that our r and c goes out of the bounds of the matrix. It might happen. So basically, if we are at 0 0 0, and if I try to do I minus 1 j, then it will be minus 1 0. So obviously minus 1 in minus 1 row does not exist, so it will give us runtime error. So we need to check for that, especially whether we have a particular valid index or not. So for that we can create a method, and in this we will receive the row index and the column index and the number of rows and the number of columns. So for the row index, it has to be at least 0, and it has to be lesser than m. Similarly, for the column index, it has to be at least 0, and it has to be lesser than n. Okay, let's also define the number of rows and the number of columns in this method. Solve. So m will be given by grid dot size, and n will be given by grid of 0 dot size. So now we need to check if this r and c is valid or not. If it is not valid, then we have to proceed to the next neighbor without doing anything for this particular neighbor, because this neighbor does not really exist. Okay, so there are 2 other cases in which we have to proceed to the next neighbor without doing anything. So another one case would be if this particular RC has already been visited in this current DFS path. So obviously the question is saying that you cannot visit a cell, the same cell more than once. So yeah, in this current DFS path, if it has been already visited, then we cannot do anything. So I need to check if RC has been already visited or not. And another thing, if this grid has zero number of gold, then also we cannot visit it, right? Because it is saying that never visit a cell with zero gold. So grid of RC equals to 0. In each of these cases, we need to continue to the next neighbor without doing anything for this neighbor, because we are not allowed to do so. Okay, so now once I have checked for these edge cases, I can basically maximize our answer by calling recursively on this R, C neighbor. Solve R, C grid and visit it. So this will give the maximum possible output with RC and this part in the, going forward with RC in this particular DFS path, right? Okay. Now at the end, what we have done is basically we have tried to traverse through all of the neighbors and found the maximum answer that we could get by going to one of its neighbors, right? But we need to remember that once we are at a particular ij, we also have to collect the gold from this particular ij, right? And we have not done that yet here. So we have not collected gold from ij right now. So once I have traversed through all this and I know what is the maximum amount of gold that I can get by going to one of its neighbors, and I can just add the additional amount of gold that I was meant to get anyway from this ij cell, which is grid of ij. Then I can safely return answer. So in the main function that we have given, again we can define the number of rows and the number of columns, right? And we need to define this vector, this boolean grid visited, that keeps track of the cells that we have visited in a current DFS path. Okay. Now what we are going to do basically, the question said that we can start at any cell in the grid that has some non-negative gold, non-zero gold, right? So we have to essentially traverse through all of the cells in the grid and first check, okay, does this grid have non-zero gold? If yes, then it can be one of our possible starting points, and then we can start this recursive function from this particular cell, and essentially it will give us some answer. So some answer that has I, j with I, j as a starting point, right? Okay, there's also another thing that I forgot to do here, which is in this, we once before calling for RC, basically the neighbor, we have to mark it as present, right? Otherwise it will keep going on and on. It will keep coming back to RC, and obviously we are going to run into infinite scenario here. So we have to mark RC as present, so such that in this current DFS path we do not run into RC again. Now once I've called for RC as a starting point in this current DFS path, we need to backtrack and make RC false. Now this is very crucial in this particular problem, because why are we basically doing this? You might say that, okay, I have visited RC and I have marked it true. Why do I need to make it false again? So the main idea is, yes, we can say that from I and j we have visited RC and we have considered all of the paths that are possible, right? But mind you, by going from ij to RC, it might happen that we might come from another cell, let's call it some R1 C1 to RC, and we have not considered those kind of paths, right? So in order to consider those kind of paths, we need to make visited of RC again false, so that in the future while running this algorithm we might come across those kind of paths. I'm not saying it has always those kind of paths, but it might happen. It will in most of the cases, right? So yeah, that's the basic idea for backtracking. Okay, now coming back to this, we have to call the solve function for each of the non-zero gold cells. So, and also we are going to have a global answer variable, and I will just iterate over the whole grid. Now I will check if grid of j has some value that is non-zero, then I will just call this function solve ij grid visited. Okay, same thing, I need to make visited ij equals to 2. I need to mark it as present, right? And again, after this, I need to backtrack and make visited ij equals to false. Why? Because in this scenario, we have considered all the paths that have ij as a starting point. But there might also exist some paths that have ij in it, but not as a starting point, right? We might start from I minus 1j, then come to ij. So in order to consider those kind of paths, we have to make visited of ij equals to false again, so that we can, when we come across those kind of paths, we do not, ignore those kind of paths, because those paths might give us a best possible answer, who knows. So yeah, in this way we are basically considering all the paths that are possible, and in the end we return answer. Okay. It should work. Yeah, that's about it for the problem. Now for its time complexity, it might be a little complex to deduce, but consider this. What are we doing basically? We are traversing through each of these each of these cells that have non-zero gold, and we are going to their neighbors, and essentially what we are doing is we are traversing through every path that is possible that has some non-zero gold. So let's first decide what is the maximum amount of cells that have non-zero gold, right? Let's call it k. Let k be k equals to the number of cells with non-zero gold, and each of these k cells have 4 options: either go to the left or go to the right or go up or go down, right? Each of these k cells have 4 options. So for the first cell there are 4 options, for the second cell it has a 4 options, so on up to, this will happen up to k times, right? So this happens total k times, so I can say this as 4 to the power k. So that is the time complexity, 4 to the power the total number of cells with non-zero gold, right? So yeah, that's about the time complexity. And yeah, thank you everyone. That's about it for this problem. Thank you.